Welcome to today's lecture. We're in chapter 11, which we're going to talk about cache memory. Cache memory is a kind of faster memory, and we'll slowly get into explaining some of the background of what it is. First of all, you see my slides, yes?
Yeah.
Okay, let me change the view. Okay. The memory access is slow compared to processor speed. What does that mean? That means that if I want to, if I want to access some memory, like in MIPS, that would be a load word or a store word, it's going to take longer than processor. Then the CPU can do stuff. CPU, let's say, wants to do some action or add two registers. It can do that much faster. A factor of 3, in other words, 1,000 times faster. One limiting rule is this: the larger the memory. So we talked about SRAM and DRAM and all those kinds of RAM, and we talked about which ones are faster. But regardless of which ones we use, the smaller it is, the faster it will be. The larger the memory is, the slower accessing time will be. And also, the larger it will be, the cheaper it will be. It's kind of like you buy in quantity. But you can imagine why this is, because imagine you have a very large storeroom. In order to find the thing that you need, it's going to take longer than if it's a very small storeroom. If you have a storeroom that only has 2 things in it, it'll be much easier to find things. So memory that's large is by its nature slow.
So technically, like 64 gigabytes of RAM would be slower than 32.
That's right. That's what we're saying.
So why does everyone say that 64 gigabytes is faster?
I don't know. I have to ask them. But all things, it could be that when we're talking about building memory, it could be that the overhead at that point could be the same at that size, that large size. Could be with a certain overhead. You have to build a certain structure for searching, and it could be that it's the same once you get to that size. I don't know. I'm just saying on a theoretical basis, it should be that smaller memory is faster. I mean, yeah, that is the rule. May not in reality always be true, but that is a theoretical rule.
So when we say more expensive here, we're talking about like price-wise, or like?
Yes.
Like it would cost more in the store, like if you go buy it?
Yeah. If you're building a computer, if you go to the factory. CPU performance is seriously impaired if for every memory read I need to have the CPU sit idle. In other words, if it takes 1,000 CPU cycles to read something from the memory, let's just say, then the CPU would have to wait there for 1,000 cycles before it got the memory that it wanted. So therefore, we don't want to use memory. We want to create a large memory and make it cheap and fast. Large, fast, and cheap. We want everything. The solution is to create a hierarchical memory system. And what we mean by hierarchical means we have different levels of size, and it's almost like a pyramid. The cache is the smallest, is the top of the pyramid. The main memory is larger and slower. The disk is larger and slower. And the backup is larger and slower than the disk. So cache is kind of SRAM or DRAM. Think about it. It's not a disk. See, this chart is a little bit weird because this is not memory at all, the CPU, and the cache and the main memory are really not a type of memory, but a purpose. And the disk is a type. It's also a purpose, but it's a little bit confusing. So what this chart is showing is that it's faster over here. The cache is faster, and it's slower over here. It's also smaller. The cache is smaller memory, and this is larger memory. So this is larger. The main memory is larger than the cache. Price, the cache is more expensive than the main memory. So when you buy a visual, what is it called, a video card, you want to know how much cache it has in it. That's to help make it go faster. The more cache, the faster it'll go, or the more ability it'll have to use fast memory.
But
You can also ask how fast exactly is the cache. And on one hand, you want more of the cache because the cache is going to be always faster than the main memory until it gets to a certain size, and then it'll become slow again.
So cache is maximized by a certain amount of memory because at that point it'll more or less become the same as RAM?
Yes, that's pretty much what I'm saying. I mean, it might be different because if you remember, we learned about SRAM and DRAM. It could be that the cache is SRAM, which is a little bit faster than DRAM. It could be your main memory is DRAM and your cache is SRAM. It could be. I mean, but we're not really discussing what exact implementation, what hardware it actually is, what the cache's hardware is. We're just saying, we're putting out there as an assumption that cache is some kind of memory, which because it'll be small, it'll be faster. And it'll be what's called close to the CPU. And the close is the sense that if I want to run there and get some data, it'll get back to the CPU faster. So it's as though it's nearby. And the main memory is a little bit more distant. The disk is even more distant. Well, okay. Now, if you notice, it's written here in Hebrew, block. Block means block. And block means a group of memory. In other words, the main memory is, let's say, a gigabyte. But I'm going to divide my gigabyte into blocks of each one, let's just say for the sake of argument, a megabyte. So then I can say, but I'm not talking about physically dividing it. I'm talking about conceptually dividing it. We could, of course, physically divide it, but we can also just conceptually divide it. If I have a gigabyte of data over here and I divide it into 1,000 in blocks of size 1,000, or really 1,024, I'll have, there's 1,000, this is a gigabyte, 1,000, if I divide it into megabytes, sorry. So how many megabytes are in a gigabyte? 1,000. So, or more or less 1,000, a little bit more than 1,000. But my block size will be now a megabyte because I've divided my memory conceptually into units. Now, what does that do for me? Every time I want to put something from main memory into the cache, I will transfer it. But I won't transfer a byte. Let's say I'm interested in a certain byte. I won't transfer that byte because then I would, if I want maybe I'm going to want the next byte and the next byte and the next byte. So what I'm going to do is I'm going to transfer a set of bytes, otherwise known as a block. In other words, if I have a particular byte that I'm interested in, I will figure out which of the 1,000 blocks that I've made over here it's in, and then I will copy from the first address of that block all the way to the last address of that block every single byte in that block. I'll copy it into the cache. And now when I want to get to that byte, the CPU will go directly to the cache and it'll find it and it'll be faster. Because you didn't have to go to main memory.
Cache in this case would be 1 megabyte?
What?
In this example, the cache would be 1 megabyte?
Well, minimally it would be 1 megabyte. But theoretically, the cache could be larger. It could have the capacity to store 2 blocks or 3 blocks or 4 blocks. I could have a cache of 4 blocks. My main memory will be 1,000 blocks. And if I want to access something, I'll first make a copy of it, which means it'll reside in both locations. And I'll now have that 1 megabyte in the cache. And it could be, if my cache is, like I said, let's say 16 megabytes of cache, then I have 16 blocks that I can put here. Which
And
means that if I, what?
Every time it would have to copy 16 blocks, or it has an option to copy only 1 block, even if there's...
No, it only copies 1 block at a time. I ask for a particular, my program goes into the CPU, and according to my program, I say, please access array at this particular location, and it says, oh, I need byte number 130,000. So that byte is in block number, 50 of the 1,000 blocks. It's in block number 50. So now I'm going to have to load that block into the cache. Now the whole block where that address was sitting is in here. All of block 50 is here, and then I'm going to read whatever I want from that block. And if I want to read the data that I said before, and then the one after it, and the one after it, well, I've got them all there because I've loaded the whole block. I've loaded like a bundle of bytes that are nearby the byte that I want, on the assumption that probably if I wanted that byte, I'm probably going to want the next byte and the next byte, because probably I'm doing some kind of a search through the array, and I'm probably going to need to use all the bytes in that area. So I'm going to take the whole, by nature, I take the whole block. And now that means that at this point, if I had 16 megabytes, my cache has only one block in it, and the rest are all empty. If there's a jump in my program and he wants to get some other memory, he jumps over somewhere else, or he has a pointer to some address somewhere else, he needs some other memory, other data in the memory. So I'll have to load another block. And since I still have space, I can load another block and another and another every time he needs something. It could be I'll run my whole program and I've only loaded 3 blocks into cache because that was all I needed. Could be that I load all 16, and then he asks for some other memory somewhere far, far away. I'm going to have to load that block in, but I'm full. So then I'm going to have to remove something from the cache. That is the basic concept. And the CPU talking to the cache is going to be faster. So I want to keep things in the cache. Cache is like, it's almost like C-A-S-H. In French, you say a cachet. It comes from the word cachet. Cachet means like a store. Like I have, if I'm a teller in a bank, I have some cash, C-A-S-H, in my drawer in case people, need to deposit or take out. I'll have some money. But if somebody comes in and wants $1 million, I'm gonna have to go to the vault. But I keep ready close by in a near source. So I don't have to keep going. I don't want to keep all my money in the vault because I'm going to have to keep going there all the time. I'll just take out a bunch of bills and put them in my drawer, and then I can deal with people. And only if I run out will I go to the. It's not exactly the same, but that's the basic idea. Again, we always transfer in blocks. So the cache is divided into units of 1 megabyte, if that's our block size, and so is our main memory. Of course, this is all conceptual. It's not physically divided. Data moving now from this cache to the CPU will always be one data word, because the CPU can only handle one data at a time, since it performs the operation of the data of that datum or on that data. In other words, when I want to read something from the cache, obviously it's just one tune, one datum, one piece of data is going to go to the CPU. And here a whole block goes into cache. And then as I need things, I'll read one by one. The CPU can only read in what I call memory words. Whatever its size is, it can deal with. In other words, a byte, either it's usually either a byte, 4 bytes, or 8 bytes. And then he just says some stuff which is not that important. The data transfer between the disk and the main memory is always by page. Well, that's why it's written here. From a disk to main memory is dapim, which is Hebrew for pages. And from the disk to the backup tape is by kvatzim, by files. So I copy file after file after file to my tape backup.
Do we have a backup built into our computer?
I don't know. You might. Very unlikely, but you might. I actually had a computer that didn't have a disk. When I was growing up, I had a computer. I had no disk, just had main memory.
But nowadays, every computer would more or less have everything but level 4.
Yeah.
A backup. Wait, a backup would be external hard drive, something like that, right?
No, that would no. Well, not in this picture. That would just be another disk. Backup would be a tape drive, like we talked about last time.
Okay.
An external tape drive. Okay. So he said from disk to main memory is by something called a page. So we're not going to talk about now. You have a course in operating systems. You did a course in operating systems, right? Oh, you didn't. When did you didn't do a course in operating systems, right?
I don't think so.
No. Next semester, next year, semester Aleph, I think. Having a kind of teach a course that teaches some very important concepts, which is operating systems. All right, disk to backup is transferred into units of files or disks, right? Copied by files or by disk. There's a tape. You could say this tape has on it disk 1 and disk 2, or you could say which files it has on it. Okay, but that's not really that important for us. Blocks are from usually between 8 and, this is a kind of strange sentence, but between 8 and 128 bytes. In other words, I was talking about a block of 1 megabyte, but that's kind of large. Usually a block is much smaller. Pages are usually between 512 bytes and 4 kilobytes. That's the page. Remember what the page is. The page is the disk into memory. But memory into the cache is much smaller. Notice very small, 128 bytes. That's like the large size. That's nothing. You're getting the idea that the cache is quite small. Pages are usually between 512 bytes. Oh, we said that. Files are megabytes or gigabytes. Okay. The DMA, okay. It's called direct access memory. So this is a concept that you might see. What's written on the bottom of the screen there? Oh, cache in a i3 is usually 4 megabytes, and an i7 is usually 8 megabytes. Notice that's a very small number. It's 8 megabytes. It's not 8 gigabytes.
So what would I5 be?
I don't know.
I heard that i5 is very similar to i7. There's like a very small difference. So I assume that this is probably not one of the differences.
Yeah, probably. There's just examples. It doesn't really matter. I mean, there's not millions. There's lots of different architectures out there. Just giving you 2 examples to show you that it's not so large. In other words, wait a second. So let's think about this. We can almost ask if the blocks are 128 bytes and it's an i3 and it has 4 megabytes of memory, how many blocks are there in cache? That's a typical exam question. Very easy one.
How much is a block in this case?
Just what is written on the screen in front of you, 128. So 128 times 4 times 2 is 256. Times 4 is 512. Times 8 is 1 kilobyte. If 8 in 1 kilobyte, I would have 8 of these. In 1 megabyte, I would have 8,000 of these. Well, 8,024. In 4, it would be 32,000, approximately 32,000 blocks in cache. A lot of blocks. in our examples in the course, we're going to talk about places where there's like, 4 blocks in cache, because it's just a lot easier to draw than 32,000. Blocks are very small. Okay. Now the CPU, even though in this picture you don't see it, you don't see the CPU directly accessing the main memory. But imagine, if you will, an arrow going into the main memory. Also, the CPU can directly access the main memory if it chooses, instead of going to cache. Now, if it were to do this, the CPU is, in his world, all he can do is manipulate data memory. So he can manipulate, let's say, bytes. So he would go to the main memory and copy byte, byte, byte. Each one would be a new activity. He would like working with like tweezers. He would take one piece of memory and then another piece of memory, another piece of memory, another piece of memory. Each one would be a separate action. And it would be slower than going to this cache. As we said, it's slow. But let's say the CPU does want to go directly to the, or let's put it this way. Let's say the CPU says to a certain device, direct memory access is a method that allows an input-output device, like a disk drive, or like an external disk drive, or maybe that's a bad example, maybe a keyboard, to send or receive data directly to or from the main memory.
Why does the keyboard need to access memory?
Well, those key types have got to sit somewhere, don't they? When I type, I type on screen, "Hello, Mom," even before I press enter. "Hello, Mom" is sitting somewhere. Where is it? It's in main memory. Now, let's say I want to go to a file on disk. Let's say I want to read a certain file. Again, direct memory access is a method that allows an input-output device, like a keyboard, or theoretically, let's say, another good one would be a web page. I have a network cable that's connecting me to the internet, and that's also kind of input-output. I'm getting data. And it allows me to send or receive data directly to or from the main memory by bypassing the CPU to speed up memory operations. Basically, I have a task. I want to write something to main memory. Now, if the CPU would do it, he would write one by one each byte. And the CPU would be busy doing this, and it would be slow because I'd have to do byte by byte. So they built a sort of a special, smaller little CPU. It's kind of a CPU called the DMA, which, when I want to read some data from the file, let's say, or the network, I just tell it, read until you hit this signal, And the DMA will go about its business of reading and copying directly into memory. So he'll have access to the main memory, and he'll write in, and the CPU can go off on his merry way doing some other thing. We have like a dedicated memory access device, direct memory access. Or the chip is actually called the Direct Memory Access Controller, DMAC. So, for example, if a transfer of data from main memory to the cache. So what about this? I want to take them from the main memory to the cache. I can also use a DMA and not use the CPU. The CPU can do something else. If I all of a sudden decide, hey, this block is not in memory, I need to put it in memory. I mean, it's in memory, but it's not in cache. I need to put it in cache. Let me go and grab it. Now, am I going to ask the CPU to go do that? Well, he's going to do it, but slowly. He'll copy each data one by one. I can ask the DMA to do it, and he has access to the memory also, and he'll do it faster. So essentially, the DMA is there to speed up the process of writing and reading from the main memory into cache.
But when we actually want to use it, isn't the CPU going to have to access the wherever it is now, the cache, anyhow, to get it? So isn't it going to take the same amount of time to access it from the cache that it will from the memory?
No, we said accessing the cache is faster. That's our rule. Accessing cache is the fastest thing you can access aside from registers. And remember, that's where most of my reads are being done. My reads and writes are going to be done to those memory locations that I stored. Anyway, I stored in the cache. So, for example, a transfer. Fine, we said that. Note that if a block of data is size 128, that if a block of data of size 128 bytes were to be transferred from cache to cache from main memory by the CPU, since the CPU only deals in words, or in this case bytes, it could take as much as 128 accesses, different discrete accesses to access the data, one for each word. This is the reason we use a DMI to transfer data. Now, we have a dedicated piece of hardware that allows the CPU, which normally works with tweezers, to just give a command, I want this and this, and print it out to the screen when you're ready. In the meantime, he doesn't do anything. Okay, let me go on. The utility and efficiency of cache. Ideally, we want a processor with the largest and the fastest and the cheapest memory. Of course, we learned that these things are mutually exclusive. Large is slow, usually. But, as we have stated, because of technological limitations, the larger the memory, the slower it will be, and the smaller it is, the faster it will be. The goal is to get almost the fastest memory while maintaining a large size and a low cost. So we want to try to get everything. We want to build a cake that has in it everything. That when I need data right away, I go to the cache, and it's there for me. And when I need data that I know has never been used in a long time, I'll go directly to the memory. But of course, I can't do that. What I'll do is I'll store the cache. In other words, the solution is to maintain a small and fast copy of some of the data. So in other words, we're going to have this cache, which is going to be some of the data. It'll be a copy. This data is called cache. Because of its small size and speed, access time will be a lot less than other memory. Because the CPU can access so freely, it is said to be nearby. We will try to keep the most frequently used data and most recently used data. We will try to get the frequently used data or the most recently used data as frequently and as recently in the nearby memory, right? Theoretically, what should I be keeping in the nearby memory? I should be keeping the things that I use frequently. Or the things that I use frequently, maybe those things, but I also should keep maybe the thing I just used, because maybe I'm going to use it again. If I just use it, probably I'm interested in it. So I'm use it again. So we have two things, most recently used and frequently. It could be half and half. Half of the stuff that's frequently used, there's obviously going to be a lot of overlap. If it's frequently used, I probably recently used it. But there could be something that's frequently used, but it hasn't been used in a month. But he's going to come back in a month, and then the whole thing changes. Fine. So we have these two concepts, basically. I'll explain this. One's called locality of time, one's locality of space. Locality of time means, what things do I want to keep? I want to keep the things that are in my time locality. In other words, things that I recently used. If I recently used this other block, I'm not going to throw it into the garbage. I'm going to take a block that I haven't used in a long time. The oldest one there, I'll get rid of first, and he'll free up. Because if I haven't used it in a long time, I'm probably never going to use him. So that will be locality of time. Figure out what the time rate. In other words, I want to maximize how much of the code I can get in the cache given a certain time frame. In other words, if I want to keep all the data that I use in the last 5 minutes, I might need 10 blocks. If I want to keep all the data I use in the last 20 minutes, I might need 30 blocks. If I want to keep all the data that I've ever used, so I might need an infinite amount of cache, or as big as the memory. Um, okay. And then we have the other concept which is called locality of space. What is locality of space? It means that it could be that I didn't use this data very much, well, recently, but it's right in front of me. I'm probably going to use it next. Like if I'm going through an array, I'm probably going to go to the next element in the array. So locality of space means if we access a certain data, we'll probably access the data next to it also. In other words, I want a certain region of the memory. So that we achieve that with the block. If I ask for certain data and I say give me its whole block, more times than not, I'm going to have all the data to the right and to the left of that one that I wanted. Theoretically, you could be at the very last one of the block.
Does it copy any of the let's say the code in our example from before, or only from that line and after?
What example?
Like, no, I'm saying like in our where we said how like in the locality of space, I think it was that one. You're saying how it copies like other stuff that are in its area. So does it like how does it like decide what's in its area? Only what's after, or like what's before?
No, whatever it's in its block. We're going to take a whole block. We're going to take, let's say, block number 1 from memory. So, and we wanted inside of block number 1, remember there's 128 bytes there. We wanted byte number, for example, we wanted byte number 10. Well, since we're taking the whole block, we're going to take 1, 2, 3, 4, up until 128. So we're going to get all the area around 10, even though we never use those ones.
So it could be any of the above said. It could be either the last of a block, the beginning of a block, or the middle of a block.
Right. But the truth is, we're actually here talking about which blocks to store. In other words, remember I said before that it could be that all of our cache is full now, and now we want another one. Which one are we going to sacrifice? We have 16, for example. My example I gave was we have 16 elements in our cache, and we want to put a 17th one in, but there are only 16 spaces, so we've got to remove somebody. Who do we remove? So if you're only interested in locality of time, you would use whichever one. Well, which one would you remove then? If you're only interested in locality of time.
The one that we use the least recent.
Right, the least recently. Exactly. Not right. That we would get rid of the one that we used the least recently. Not necessarily the first one to have come into the memory, into the cache. It could be somebody came in and then it's not a first come first serve or it's not a FIFO or a LIFO. We got to keep track of when they were last accessed. You realize that to do locality of time and to decide on that basis means that we'd have to keep track of when all the accesses were for every block. The other possibility is locality of space. What would we do there? If we had 16, which one would we get rid of? We want to bring in 17. Which one would we get rid of? We only are interested in locality of space, not time. If 17 was at location, was block number, it is block 17. The block number is 17. We want to put block 17, but let's say it's block 17, but there's only 16 places there, and they're all full. So who are we going to remove? And who are we going to keep? We're going to keep if we're going to keep 15 and 14 and 17. Well, 17 is what we're adding, and 16. But if we see that one of the blocks in there is block number 123, we'll say, oh, that one's far away. I'm probably never going to use that one again because I'm over in block 17 now. Probably going to use the blocks around it, like 16 and 15 and 19. So, but if we would use both parameters, we would look at both things and try to decide. We'd give a weight to each of those factors and decide which one to remove. So if we've talked let me show you a picture. No. Yeah, here's our cache. Here, for example, there's rows and rows of cache. Each row is, let's say, a block. That's all I want to show you. Now we talked about that I want a certain memory inside of a certain block. That block is either in the cache or it's not in the cache. If it's not in the cache, I'm going to have to go get it from memory, put it into the cache, and then access it. So we can talk about something called a hit. A hit is that the data that I'm interested in, the particular byte, is in a block in cache. Now, it's housed always, of course, in a block, and that block is in cache, then it's a hit. A miss would be when the block is not in cache, it's just in main memory. And obviously, if I have a miss, I'm going to have to import that whole block. So we can talk about what's the hit rate, the number of accesses where the data is in the cache divided by the total accesses. In other words, 9 times out of 10, I went to the cache and I found what I was looking for. I didn't have to go to the main memory. So 9 times out of 10, that's the number of times we access where 9 times. Out of the total access, out of 10 total accesses, which means that there's a miss rate. And the miss rate is the number of misses divided by the total number of accesses. So that'll be 1 over 10, or 10%. Which makes sense. 10% of the time I miss. And 90% of the time I hit. And now you can say, well, then therefore we can say the miss rate equals 1 minus the hit rate. I mean, it's just obvious observation, but it's true. Because the miss rate, if 10% of the time I have a miss, then if the hit rate is if the hit rate is 90% of the time, then 1 minus 90 is 10%. So the miss rate is 10%. Must be. Hit and miss rates are dependent on the particular program being run and will change if a different program is tested. Right, because it could be that I have a lot of hits because my program is always accessing code nearby. It does like a loop 1,000,000 times over 3 lines. And it keeps on accessing data right next to there. There's the code itself is data. I just keep on staying there. I have other code that has these jumps. And it jumps from here to there. And therefore, I'm going to have to keep the location. I'm going to have to keep many more caches in many more blocks in my cache. But assuming the cache is equal, eventually, it's equal size in both cases, whether I had to jump around a lot or I didn't have to jump around a lot. I'm going to have a problem with the one I have to jump around a lot. A lot of times I'm going to jump very far away. And because I'm interested in locality of space, the block is not going to be there because I only have the blocks from nearby. So I have to put it in. So you can see that the miss rate, my point is just this, that the miss rate is dependent on which particular program I'm running. It is not the miss rate of this architecture. It's the miss rate given a certain program. Yeah, question.
Is the code always stored in the cache?
It's always stored in main memory.
No, in the cache. Does the cache always have the currently running program code?
Theoretically, no. Practically, yes. Theoretically, I could. I'd have to have at least. Yes, sorry, I take it back. I have to have at least copied. Yes, the main memory doesn't. The CPU does not read directly from memory. It reads from the cache. So therefore, since it's reading lines of code, the lines of code have to be in the cache, but not the whole program. Just the section where I'm reading, just the blocks where I'm interested in reading.
So based on that, originally, first of all, the code itself is first of all stored in the disk, then it's copied to the memory, and the current part that's being run is copied to the cache.
That's right.
So also cache efficiency, is that dependent at all based on the actual hardware, like based on the actual cache, or it's completely dependent on the program that's being run?
If we didn't talk about cache efficiency, I don't know what you mean. You mean hit rate and miss rate? Or you mean like how fast it is?
No, like it doesn't. This is titled cache efficiency.
Oh, right. Terminology for evaluating cache efficiency. Right. It means, but it's not the speed of the cache. That's not what I mean by efficiency. What I mean is how effective has it been over the course of this program?
So I'm saying, is how effective it is dependent on the hardware at all, or it's completely dependent on the program that's being run?
No, it's completely it's not dependent on the hardware because I mean it's dependent on this again, we're talking about the hit rate and the miss rate. That's not dependent on the hardware. It could be that a hit is dependent on the program. Did I find it or did I not find it?
But I'm saying, like, for a same program, do you have one cache that will have a higher hit rate than another cache?
Yeah, you could have a different, not because of the hardware being different so much. I mean, it could be the hardware is different, but it also has to do with whether the design of the cache is different. Let's say like that, the hardware being different. But we're going to talk about the design. Depends what you mean by hardware. In other words, it's the same nails and the same wood, but did I build a bed or did I build a bunk bed? Did I build, you know what I mean? The hardware in a certain sense is the same, but how I arranged it, how I built it is different. So that's really is different hardware in the end. So yes, it is dependent on the hardware, which is methods of implementing the hardware. We're going to talk about that. For example, if I had very small cache, my cache only had one block in it, which would be the minimum, then I would have a very high hit rate, miss rate, because a lot of times I would get to the end of my cache and then I mean, anytime there's a jump to some other place in memory in my code, then I'm going to be executing different code, different place. I'm going to have to bring that block in. And if I jump back, every time I have a function call, for example, I might have to bring in a new block. So I could have a much higher miss rate if I only had one. If I had lots and lots of blocks in my cache, then I'm going to have a very low miss rate because I have so many places in there. I'm probably going to have everything that I need. But it could vary from program to program. More terminology. It's something called a block. A block is a unit of bytes by which we divide the cache and main memory. We talked about a block all the time. Now we're just defining it. It's identical for both. In other words, the block size, if it's 128 bytes, that means I'm dividing the memory conceptually into into units of 128 bytes. And also I'm going to divide the cache into the same unit size. Now we're going to talk about two more parameters. Something called the hit time. The hit time is how much time it takes, like in seconds or nanoseconds, the time it takes to either read or write a data to or from the cache. In other words, the hit time. It was a hit. That means I found it in the cache. Now what's the time? How long does it take to read that data? That is the hit time. When I had a hit, how long did it take me to get the data? That's one parameter. Another parameter is the miss penalty, which is the time it takes to bring a block from main memory to the cache or to write it to main memory to main memory from the cache. Either way, either direction, I'm importing it or exporting it to or from the main memory. And that's called miss time. In other words, the time or miss penalty, the time I have to waste because I had a miss. As I got to go and get it from main memory. If my cache were just bigger, I wouldn't have had this miss. I would have saved time. So that's the miss penalty. And as we have said, when the processor reads from cache, it reads one datum. But when we copy data into the cache from main memory, we copy an entire block. All right, we said that. Now here's an equation for evaluating efficiency of hierarchical memory for a specific program. So this is for a particular program. And we, fine. Average memory access time. The average access time is going to be some kind of combination of the hit and the miss. Sometimes I get a hit and sometimes I get a miss. So let's look at the right side first. It's the miss rate, how often I miss, times the miss penalty, times how much it costs me when I miss? How much time does it take to go get it from the main memory and put it into the cache? It should be that, and then it should be really the hit time. It should really be hit time times the hit rate. How often I get a hit times the time that takes. And then it should be the combination of those, because those two, the miss rate, remember, is the 1 minus of the hit rate. So I should have the hit rate here times the hit time, and that'll be 100% of the time, and it'll be this amount of this and this amount of that, and I'll get the total. Why doesn't he write here? Is it wrong? Can anybody think of why it doesn't say here the hit rate also? It should logically be the hit rate times the hit time. How much of the time do I get a hit and how long that takes? Plus how much time do I get a miss and how long that takes? That's not correct. This is correct. What does that mean? Nobody can think about it. So the hit time, it's like this. When I go to the main memory, when I jump over to the main memory to get something, because I had a miss rate, I bring it back into cache, but I also now have to read it from cache. So now it becomes a hit, even though that gets counted in the column of misses. In a miss column, what do? I do the miss penalty, which is going and fetching it, times how often this happens. But I also do a miss rate times the hit time, because included in a miss is the eventual hit. When I've loaded into cache, now I can hit it. So I should have, it really should be miss penalty times miss rate plus hit time times miss rate. And over here, it should be hit rate times hit time. So hit rate times hit time and miss rate times hit time. Well, that together, we know that hit rate and miss rate together is 1. So I just write 1 times hit time, and I've got the same equation. In other words, this hit time is 100% of the time I have a hit, because even when I have a miss, eventually I bring it into cache, and then I got to do the hit again. So the hit time is 100% of the time. It's only the miss rate that affects, that adds up to that makes things slower. Okay. Methods for mapping blocks from main memory to cache. So there are different methods for mapping. Mapping means deciding where to put a particular block in cache. Up to now, we just said, okay, I have a picture here. I have a good picture. If you really make a picture. Anyway, basically, we sometimes are going to be putting things into blocks into the cache, and eventually the cache will be full. Fine, we talked about that. But now I have a different question. Where am I going to put it into the cache? Should I just put it anywhere? Can I just put my block? I'll put block number 7, then I'll put block number 1. Then I'll put block number 15, then I'll put block number 2. Is there any order of where the blocks in memory should reside in the cache? So we could do it on a theoretical basis, that we put every every memory block into anywhere we want in the cache. And then how are we going to find, if we're looking for a particular block, how are we going to know if it's in the cache? Well, then what would we have to do? Can anybody think of what we'd have to do? How do we know which ones are in the cache now? I put all kinds of random blocks in cache, and how do I going to know if the memory that I'm interested in is in the cache or not? First, do you see the problem? Does anybody see the problem?
Are you able to go over the problem again?
Yeah. I put here, maybe I'll draw a diagram. Let me do something. Here's my memory. Which block is this? Anyone can guess what block that is? That's block
Number
0.
1.
Okay, we can call yeah, you can call it number 1. We can call it number 1, or we can call it number 0. I'll call it number 0. Either way. And this is going to be block 1. This is going to be block 2, etc. This is going to be block, n. And here's my cache. Now I could have theoretically here any block. I could have block, block 17, block 2, block 14, block 0.
But in
Now
memory, the blocks are divided in order.
In memory, they're divided in order, exactly. So therefore, if I want to get, let's say I know that my blocks have 128 bytes in them. So here, let's say like that.
Is anything copied back from the cache to the memory?
Yeah, we'll get to that. Let's not talk about that now. But yes, we'll get to that. Let's say each block is 128 bytes. So if I want, let's say, data number 258, which block is it in? Address number 258. Or I'll start easier. I want address number 0. Which block is it in?
0.
Very good. I want address number 1. Where is it?
Where? 128.
No, I want address number, byte number 1.
Block 0.
It's in block 0. Address number 2, where is it?
Also in block 0.
Also block 0. What about address number 127?
Block 0?
Yes, block 0. Address 128, where is it going to be?
2.
1.
Block 1. If I want to address 257, where is it going to be?
Block 2?
Block 2. Which byte will it be in block 2? The first byte or the second byte?
Second byte.
Second, exactly. The first byte will be 256. Second will be 257. So if my CPU says, give me a byte number 257. He doesn't care about blocks, doesn't care about if the CPU just wants to, the CPU wants to go directly to memory, which he's allowed, he'll just jump right into 257. He'll be in block 2, but he doesn't even care about the block, but he knows exactly where to go because these are in sequential order. He knows exactly where to go. I don't store the address here of each byte doesn't have another byte that tells you what it, and as we don't put a 4-byte address, attach it to every single byte. We know where that would be a tremendous waste of money. We would have every byte that we would have, we'd have to have 4 bytes to take care of it, to tell me what this address is. The address can't be bigger than the thing we're addressing. So there is no address, actually. It's just where to go, which physical line to light up, and which address in which I light up the 257th line, and I'll get that data. But when we're talking about cache, how am I going to know where? I just said that 257 is in block 2, but now I'm going to cache. How am I going to know where to find it? How am I going to know if it's here in the first section, second section, third section? How am I going to know that block 2 happens to be here? In the first case, I didn't need any extra information. I had physical wires connected to the memory, and it just lit up that wire in order. It just lit up the 257th line, and boom, I got out the address. Here, I can't do that. If I lit up the 257th line, first of all, I might be out of the. I'll be over here, block 14. I don't want that. So how am I going to get it? Well, what's the simplest solution?
You keep a part of it that memorizes where it is, like a pointer, so to say.
Yeah, well, kind of, yes. I'll do like this. Come on. I'll do like this. I'll say here, well, I could write different things here. I could either write, like, for example, I could write 256. And I could write here 0. And here I would write, well, that's hard to know. Well, let's change this to 4. What's 256?
512.
Yeah, 512. Thank you. I'd write 512 here. And then I would know. He says, oh, I want 257. I'll just go and look. Is it here? Well, obviously, I'm not going to find 257 here, but I'll find 256. And if I know that the block size is 128 bytes, then I know that if I got 256 here, I know that somewhere in here will be 257 because the blocks are that size. And also not only 257 will be there, 258, 229, 230, 260, 270, 300. They'll all be here. So that'll work. I'll have to store the address, essentially. In other words, I could also do a different way. I could store the block number. I could just write the number 2 here and write the number 4 here. That's not 4. And then I could also calculate. I can say, oh, what does 2 mean? 2 means the second block. Well, I got to multiply by 256, that by 128. I'll get 256. Oh, 257 must be here, block 2.
That way seems better because then we could change it based on how many bytes a block is.
Well, we're going to set up a system. We're going to build, again, for the CPU to know this piece of information means we're not changing it. The CPU is going to be built to know that. You see what I mean? It's going to be hard-coded in. We're not going to change it on the fly. So that's not really, doesn't help us. What it does help us is it's smaller. 256 is, I mean, we can think about the advantages, disadvantages. The first way I did it, I didn't have to do any computations. I could just jump immediately as soon as I found it. The only thing is I have to store how many bytes do I have to have here. I have to have 4 bytes. This way I can have fewer bytes over here, but I'll have to do a computation. I'll have to multiply this by the size of my block. It turns out that this will be faster. I don't actually have to do the multiplication. There's a trick. There's a trick which we'll see, that this will be faster. But there's still a problem here. What's the problem? Can anybody think of the problem of this system? Well, how did I find 2 that it was over here? How did I know to go to this line? Did I go there immediately? No. First I went to 17 and it wasn't right. Then I went to this. I'll have to build some kind of search. Well, actually, I can build a parallel search in hardware, which will be fast. I won't have to search. I'll search simultaneously in every location. But it's still a search. It means I'll have to have a lot of wires. I'll have to parallel wires, and I'll have to check every single place. Is it the right one?
But this you will have to do even if you store the byte location, no?
Either way. I said it's a problem with both systems. Whether I write 256 here or 2 here, I'm still going to have to check every single location. And that's a cost that we could also avoid. Can anybody think of a way to avoid that cost?
Sort them each time?
What? What'd you say?
Yeah, take it back.
Okay. Anybody think of a way to avoid that cost? I don't want to do a parallel search. I want to know exactly where the block is immediately. Well, the only way to do that is not to just put them in random places. I can't just put 17 here and 2 there and 4 there. I can't just put them in random places. What am I going to do?
Keep it sorted.
Well, sorted means I still have to do a binary search. If I kept it sorted, I'd still have to search. Because I don't know, I know, fine. I'm looking for 17. This is 1, this is 2, this is 3. I still don't know if this is 17. This could be 17. So order is not the best, but it's a good idea. I'll show you another method. I can put, for example, I can say, wait a second, I got 4 here. Let's take my memory and put it in groups of 4. In other words, I'll do modulo 4 on the block. So if I have block, this is 3, 4, 5. Let's say this is block 5. Where's block 5 going to go? He's going to be, I'm going to take 5 modulo 4, and I'm going to get 1. So block 5 will go here. And then I don't even have to write a 1 here. This will be permanently location 0, 1, 2, 3, which means I don't have to write it because it's in order permanently. It's never going to be 1, 0, 1, 17. It's going to be 1 there always. And so that location I don't even need anymore. So how do you do?
What if we have multiple blocks that are supposed to go into the same address?
Yeah, so that's exactly the problem. I'll show you that. I'll show you how to deal with that. Where is my strike through? Here. I want to put these strike throughs here. Just a second, because they're not really supposed to be there, actually. I'll do it. Just demonstrating the idea, but actually this column doesn't exist. So now I've also, not only do I not have 256 here, I don't even have 17. I have nothing. I can save that whole, but I don't have to store any data, which is wonderful. I don't want to store data. That's the worst thing. Okay, so I won't do the last one. So 5 will go here. So wait, who spoke before? That was
Me.
Eliezer. Oh, Ronnie.
Yeah, Ronnie.
So Ronnie said a good point. He said, "What if I want to put somebody else? Who else would go in this spot?
Block 6.
What?
Block 1.
Block 1, not block 6. Where would block 6 go?
Not 2.
Exactly. Block 6 would go here. Who else would go here?
2.
Who else?
Wait, why would block 6 go there? Isn't it divided by 4s?
Wait a second.
Mod 4.
Mod 4.
Mm.
Wouldn't block 10 go here? 10 divided by 4. 10 divided by 4 is 2, remainder 2. So it's 2. So block 10 would go here. Block 5 would go here. Block, what's it called? Block 3 could go here. Block 3. And block 40 could go here, for example. Just to make it confusing. Just to show you that it's what I got here is that if the CPU says, give me here, let me just write them. I'm developing the idea here with you. Instead of just jumping to the conclusion, I'm developing the idea, which I think is useful. if you want to understand why they did it the way they did it and what the alternative was. Here's cache using mod. Okay, cache here using address. This is cache using address, kilo, block address. And that's of course a bad method. And this is a better method is cache using modules. So I don't have to record this. And I know exactly where 40 is going to go. If the CPU says, hey, I need something in block number 40. Why block number 40? Because he said, well, I need some large location, some memory address. He took that memory address and he divided it by 128 bytes, and he got 40. He said, oh, he got 40, he got 40. So he knows it's in that section. So he goes to 40. When he wants to know where is 40 going to be, he takes 40 and he divides it by 4, and he gets 0. So he says, oh, it has to be 0. But guess what? 40 isn't there. Block 0 is there. How is he going to know that block 0 is there? Actually, we are going to have something like this. We actually are going to have. How is he going to know which one is there? It could be 40, it could be 0. So we actually are going to have these. We are going to have. It is going to end up looking kind of like this, actually. But the trick is, so what we didn't gain. So I take it back. We didn't gain the saving of this space here, the address. We're still going to store the 17. But in other words, we don't have to have the 17. But now the order is not random. So when I say, for example, this is going to be 40. Oh, that was a mistake. Now I screwed myself up here. But this is going to be, I think I have to get my plug. This is going to be 40, and it'll tell me it's block. This is the actual contents of block 40. So what did I gain over this method? Did I gain anything over this method?
It's more randomly assigned.
Which one is more randomly? This is more randomly.
No, the blocks, meaning it's.
No, this is pretty random. 17, 2, 4. There's no order here. What did I gain? What did I gain in speed? How is this faster? I said it in the beginning, actually.
You don't need to search.
I don't need to search. The minute I know I want block 40, it can only be in this line. Block 40 can't be here, it can't be here, it can't be here. Because 40 modulo 4 is 0. It's got to be on this line. I don't need to search at all. Either it's there, either I get a hit or I get a miss. No two ways about it.
Why did we switch that to 40 instead of 0?
Because 0 is van meelav. 0 is obvious. This is the 0th line. This is the 0th, the first entry in our cache. So it's obviously everything in the first entry is going to be whatever the address is, modulo 40, modulo 4, whatever the block number is for modulo 4.
I'm saying, does it actually save 40 there? Is that saved there?
Yeah, that we're going to actually now have to save. That's why I took away that's why I took away the cross out. It's going to have to store this now. Because how else are we going to know that it's not 5, that it's 5 and not 1? We have to write a 5 over here. We're not going to write it is true that I cross out the 1. I'm not going to write the order. The order is obvious, but I'm going to write the crossing out what I did before is correct. In other words, there's no 3 there. But what there is the block number. In other words, I don't write 0, 1, 2, 3. This location is location 0. This is location 1, location 2, location 3. So block 10 can only be on this line. Also block, 2 can be on that line.
Did you explain already how to solve doubling problem?
What doubling problem?
If we need to put both block 10 and 2 in.
Well, we've lost that ability.
Or we
That's
can't
exact-
do it.
we
That's
cannot
not
do that.
solvable.
That's the catch. Here we could have both block 2. If I could have block 2 and block what did we say? Block 10. Right? They have the same modulo. Let's change this to 10. And this would be 10. Over here, I have more flexibility. I can have block 10 and block 2. Here, I can only have one of them. I can't have both.
So I'm assuming that the reason we use modulo and not divide, because that way we could have consecutive blocks.
I don't know what divide would be. We didn't ever talk about divide.
No, meaning like I'm saying modulo 4 instead of divided by 4. 'Cause then you wouldn't be able to have.
We never did dividing by 4. We divided by 128 to figure out what block number it was. Let me get my electric cord. Okay. Question, Yitz?
No, it's good.
It's good? Okay. So what we've gained is that it's faster. We don't have to search, and which essentially means we've saved. It's actually not so clear to me why this is so good. I mean, in our example, we can say, well, this would be great because I can just build I can put it everywhere I want. I could have 2 and 10 in memory if I want. But I have to build the logic gates to be able to search parallel everything. Well, if it's only 4 lines, it's not a big deal. I can search everything. But if we just said that we just figured out that it's 30,000 lines, if you remember before, we talked about how it's the average size, size could be 8 gigabytes, and each one is only 128 bytes, and it comes out 32,000 lines. So then we'd have a lot of parallel searching, a lot of wires, and that would be too much. So I don't know. Maybe that's the factor. But in any case, this method allows us to avoid searching, but it does create this other problem of not being able to have ones that are happen to sit on the same location, like 2 and 10. But maybe this is what you meant, Isaac, because we said before there's something called locality of place, of space, which means that I'm probably not going to need 2 and 10. I'm probably going to need 2, 3, and 4. If I'm running my program, I probably am staying in a certain location in the memory. I'm not jumping all around, and I don't happen to jump on the exact same 2 spaces that I need. I don't happen to jump in 2 and 10. I'm not going to keep needing 2 and 10, 2 and 10 all the time. I'm going to probably need 2 and 3 and 4, 2 and 3 and 4. And once in a while, I'll need 7. And then 2 and 3 and 4, 2 and 3 and 4. Then I'll need 8. And then 2 and 3 and 4. So this system works well because most of the time I need adjacent memory, and adjacent memory is going to be all right. And especially if we realize that the cache has in it 32,000 lines, so I can have 32,000 adjacent blocks. So I can have a whole section in my memory, a whole large section. Only, the likelihood that I need to jump, to some other place outside of those 32,000 blocks is small. And if that happens, then, I'll lose one of my previously stored blocks, and maybe I won't even need that one. So just understand that we probably gain more than we lose in this system. But it does have a certain inflexibility. All right, now let's see. That was I just explained to you about 6 slides. So let's go look at the slides now. So this is a kind of a rough explanation of everything in what's it called direct direct mapping. But let's look at the slides. Anyway, any method for mapping cache, this is not a whole problem. This is the problem I'm explaining. Where does this block in memory go? Does it go here or does it go there? That's mapping. Has to deal with any method will need to relate to 4 questions. Where in the cache will the memory be mapped to? Will it be mapped randomly anywhere I want or only in the modulo location? How do we locate in the cache the block containing the byte we're looking for? What mathematical operations do I have to do given a memory location? What mathematical operation do I have to do to figure out where it is in the cache? Now, I'll take the memory location and I'll do division by 128 or something, and I'll figure out where it is in the cache. And then I'll do modulo 4, and then I'll get something. When the byte is not in the cache, so let's say the byte is not in the cache. By the way, I didn't draw that in the previous thing, but there's going to have to be another bit here to tell me, I can't just write, if I want to say that block 40 is not there, what am I going to do? Write 0 here? If I write 0 here, then I'm going to think this is memory block 0. So actually what I'm going to have to do is have a whole nother column over here, which tells me whether there is any memory at that location, valid or invalid. A valid bit, which when it's 0 means this is empty, and when it's 1 it means it's full. So now we can say when the byte that I'm looking for is not in the cache, we will need to load the relevant block into the cache, obviously. But if the location I need to put it in, or if the whole cache is full, which means the valid bit is 1 for every block in the cache, we need some methodology for choosing which block to remove from the cache. Which block will be our sacrificial lamb? Who will we remove and lose? Maybe we'll lose the one we least recently used. But maybe we'll have a different method. Maybe we'll lose the one that's furthest away. We could be more interested in location. We have different possibilities here. When the processor writes to cache, will the change be copied to the main memory immediately, or will changes be copied only when a block is removed from cache? What that means is like this. Now that we understand this picture over here, let's say I change something in the cache over here, whatever, whichever cache. I change something over in block 17. What do I do over here in block 17? Do I change it here and change it there every time? Well, that seems kind of dumb, because then it's going to take me time to write it over here. But it's not so dumb. Well, I could do that. I could write it here and write it here. So why I'd all have the cache? For reads. When I just want to read, the reading will be faster. The writing is true. I'll have to go here and here. But the reading, if I just don't want to change it, I just want to read it. Most of the time, I just want to read, or a lot of the time. Right? I don't overwrite my array a lot. I read my array. Maybe I want to write a lot. So the writes I'll have to change. Anyway, if I do it like that, there's 2 possible methods. One is that every time I make a change over here in cache, wherever the cache is in the main memory, I also make that change so that the cache reflects correctly. What changes are made over here are reflected in the real memory, so that the write I did is actually doing what I'm supposed to do, writing. The other possibility, and this will be a better possibility, is I don't write. I just write changes here, and I leave them here. But eventually, I know that I'm going to swap. This guy will become the sacrificial lamb. He will eventually be removed from memory. And then when I remove him, I will write him back. So then I only have to do it once. Even if I made, in the 128 bytes over here, I maybe made 10 changes, 20 changes. And all the changes I did in the cache. And then once at the end, if this block has been altered, I'll write the whole block back. Now you can say, well, I'm writing the whole block. By the way, that's what we're going to do. We're going to write the whole block back. Because we're not going to know where the change was exactly. We're just going to know there were changes in this block. We're going to have a bit called a dirty bit, which is going to tell us, has this been dirty? Has block 17 had some alterations done to it? Then it's like a paper that I've written. I had final paper, and then I wrote comments on it. I added a comma here, I put a capitalization here. So now it's dirty. I've messed it up, and I gotta copy it back. So I could wait. That's called write back. I wait until I'm finished with this cache location. In other words, I want to remove him because I want to put somebody else in. Oh, I'm removing him before I remove him. Wait a second. Check if it's dirty. It's dirty. Oh, then write it back because I got to record those changes in main memory because I'm about to lose them. I'm about to write over this. I'm about to write over cache at location 17. So I got to write him back to main memory. That is called write back. And that requires us having a dirty bit. The first method is called write through, where I don't have to have a dirty bit then. Every time I make a change here, I make a change here. And you can say, well, there's also the call. Why do I make just one change here? I'm going to have to copy back the whole block because the dirty bit's going to tell me it's dirty. It's not going to know what I changed here, but I changed something. I better copy it all back to memory. So you can say, oh, well, you're writing 128 bytes. That's going to take a lot of time. Why are you? So actually, I don't know if we didn't talk about it yet, but there's something called, or did we talk about it? Yeah, we did talk about it. We talked about the DMA. The DMA, actually, the CPU can tell the DMA, go and write a whole block back to memory. And then the CPU can go off and do other things. So we don't have to write those 128 bytes, byte by byte, because that's the way the CPU would do it normally. He would write one byte after another. But now that we have a DMA working for us, he knows we can tell him just write this whole block back to memory. And he'll do that. And that'll be fast. It'll also be fast. Faster than, he'll do it in a method that's faster than just writing byte by byte. And therefore, it won't be so costly. So the write back method in the end becomes the preferred method. The method that I described to you just now, essentially with the modulo, is called direct mapping. Because it's simple to implement, but not flexible. Flexible, that means that I can't have, two blocks whose modulo is the same. There's also something called fully associative, which is more like the one I did for you on the left. Any block can be mapped to any location in cache. This is obviously more flexible. I can have blocks that are, overlapping in a sense.
The first option, direct map, that's like which option that we learned? That's like the modulo one?
Yes. Direct map is the modulo, and the fully associative is actually the first one we did. Right, I did it in the opposite order. We're going to see the fully associative has a high cache utilization, but it's complex to implement. It's more complex to do that. And then we'll see this n-way associative, which is a compromise between the two methods. It uses both methods together. And here is what I said about the modulo. In the direct mapping, answer to question 1, we will take the block number and do modulo on it by the number of blocks in the cache. Like in my example, it was 4. So we'll do block number mod 4, and we'll get the block number. The block number in cache really means like the row in the cache that I'm interested in. That it should be sitting there. So we give an example. For example, if I have a cache a total of 8 blocks, not like my example, which was 4, let's have 8 blocks, and I want to go to block 12. So we'll do 12 modulo 8, and we'll get 4, and we know to go to place 4 in the cache. If we then wanted to load block 20, we'll again do 20 modulo 4, and 20 modulo 8, and we'll get again 4. So that means we're going to have to remove block 8 and put in block 20 in that same location. And that's direct mapping. And I'll leave it for next time to explain exactly how we divide. We're not going to do modulo. In this slide, we're going to end here on slide 14. But in this slide, I'm going to explain how we don't actually have to do the math of modulo. We're just going to look at certain bits of the address to tell us that. And I'll explain that to you next time. Okay, next time will be tomorrow in Yat Hashem.
1:30? Mm-hmm.
Yeah, 1:30.
We did have more people that joined in the middle, by the way.
We did. Okay, good. Well, I see we have 5 now. Yeah. Oh, 5? No. More. 6, 7. Yeah, okay, good. We have
We even had 9 before at a certain point.
that is pretty good. Although, yeah. Okay, great. So if you didn't see it, you can. I'll post it. Okay, Lila Tov, guys.
Thank you.